Products like this arose in the 1950s and 60s largely because of cheap oil. Plastics symbolized the optimism of post-war expansion. They were cheap, they could be made rigid or pliable, and they were light. New applications snowballed. Now 7% of all crude oil ends up either in plastics or as other bulk organic chemicals. This is the BP complex at Grangemouth, which you saw in the first television programme. It was Europe's first major manufacturing plant for ethylene and has been a major supplier to the petrochemicals industries for 30 years. Grangemouth's raw material is North Sea oil, but with only enough oil for about 20 years, what other sources of chemical feedstocks are there? One alternative is gas. This is the Brent field, a joint Shell-Esso venture. Most of the gas used to be burnt, simply because it was too difficult to get ashore, but the wastage was enormous. By 1981, the equipment required to separate the gas from the oil at the platform had been installed. Now the gas is fed by undersea pipelines from rigs in the area to a central platform, Brent Alpha. From here, a pipeline on the seabed carries the gas the 450 kilometres across North Sea fishing grounds to St Fergus in Aberdeenshire. The gas which reaches here is about 80% methane. At the St Fergus complex, the methane is separated from the other gases and supplied to British Gas, who feed it into the national gas grid. Eventually, the remaining gas, much of it ethane, will be piped underground to Mossmorran in Fife. Here, the ethane will be converted to ethylene in a massive new £400 million complex. By 1985, this barren landscape could be the source of 500,000 tonnes of ethylene per year. But, like oil, gas provides only a medium-term solution to the chemical feedstocks problem, perhaps 25 years. But we do have another alternative. Britain has large reserves of coal, some in areas as yet unworked, enough to last 300 years at current rates of use. Products such as benzene and early plastics did originate from coal, but its role as a chemical feedstock was largely replaced by petroleum. So in principle, it could substitute for oil.
It's high time that we started to develop the coal industry, not only in the sense of power station coal burn, not only in the coking industry, but also looking at what we can extract from coal. There is nothing in this office, there is nothing that we wear, there is nothing that we have in our home that cannot be produced from coal. It cannot be extracted from coal. It's high time that the scientists started to extract this and then leave us with a byproduct that we could use as a fuel.
That was in 1975, and since then research has borne out the principle at least. Coal board researchers have developed a unique process in which coal is converted into a liquid form by a combination of solvent extraction and hydrogenation. The hydrogenated product can then be refined by distillation into both fuels and, more importantly for us, chemical feedstocks. The process is being carried out on a pilot scale at the board's coal research establishment near Cheltenham. This is powdered coal. It's added to a vessel containing the solvent, and the mixture of coal and solvent passes through a heating coil suspended in a fluidized bed of hot sand. The hot mixture is then stirred for an hour to dissolve most of the coal. Undissolved coal, about 10% of the carbon and all of the mineral matter, is filtered off. This is still useful as a fuel for industrial plants. At this stage, we have coal solution, a tarry-smelling liquid which contains the dissolved coal as complex aromatic compounds. The next step is to turn this into lower molecular weight products by hydrocracking. Coal solution is mixed with hydrogen gas and passed over a catalyst in this stainless steel reactor. High temperatures and pressures are used. To prevent heat loss, there's an insulating jacket. After hydrogenation, the material is distilled. The distillate passes up the fractionation column, and a light fraction condenses containing liquids boiling at temperatures up to about 250 degrees. From this light fraction, simple conventional treatment gives various fuels and naphtha for use as a chemical feedstock. The residual heavy fraction, which contains partially hydrogenated compounds, is recycled. It becomes the solvent for the next addition of coal powder. This is a pilot-scale operation producing only 10 kilos of distillate per day. So how far away is a commercial plant? CRE's Doug Davidson.
I would think probably a decade away. The middle 1990s is the most earliest date at which one could sensibly build a commercial process stream based upon British coal and our process.
While Britain seems reluctant to invest in coal as a feedstock, countries without oil have invested massively. In South Africa, 2 plants on this scale have been constructed in the past 5 years. This is Sasol 2 near Johannesburg. It's one of several gigantic processing plants which turn coal into fuel and chemical feedstocks. The principle, though, is quite different from the one used in Britain. A 2-stage process is used. First, hydrocarbons in the coal are converted into gas in one of these 45-ton gasifiers. Here's the principle. Coal is fed into the top of the gasifier. Steam and oxygen are injected into the gasifier at the base. As the mixture passes over the coal, partial combustion occurs. The steam reacts with the partially burned hot coal, producing hydrogen and carbon monoxide, which emerge as gas, so-called synthesis gas, at the top. After scrubbing to remove impurities, the synthesis gas is fed to the synthesizer units. In the presence of a catalyst, the hydrogen and carbon monoxide react to give a mixture of hydrocarbons. After leaving the catalyst, the resulting hydrocarbon mixture is led off to be refined. A measure of the importance of the Sasol plants to the South Africans is that they have become an important target for the banned African National Congress. These are Sasol fuel storage tanks sabotaged in June 1980. So, coal may provide those countries which have large reserves with a secure source of chemical feedstocks for the medium term and even longer into the future. But what about countries with no coal? And anyway, what happens when our coal runs out? Ultimately, we shall have to rely on renewable resources, and that in turn means relying on the products of photosynthetic solar energy conversion, green plants. On a small scale, we already do make use of plants. The roots of certain Mexican yams contain the sterol diosgenin, used for the synthesis of some steroid hormones. Sterols are also extracted commercially from some green plant crops. However, the main products of green plant photosynthesis are carbohydrates. Much of this is in the form of cellulose and other polymers. But all plants contain some sugars which are readily accessible, and one of the richest sources of these is sugarcane. In fact, ordinary sugar, sucrose, is the largest scale organic chemical extracted from a renewable resource. World production is about 90 million tons per year. Most of it is used for food, but it could be used as a chemical feedstock. From maize comes another sugar, glucose, used on a small scale as the feedstock for making one of the most important pharmaceuticals, penicillin. This archive film shows how it was discovered. Legend has it that Alexander Fleming was examining some old bacterial cultures. One plate had a mold on it, a penicillin species which shouldn't have been there at all. But, so the story goes, he noticed something surprising. Around the mold, there were no bacterial colonies. Something from the mold was lethal to them. That something was penicillin. It was commercially exploited in time to be used on wounded troops in the Second World War. It was given in massive doses to prevent bacterial infections. Mortality among the injured was reduced enormously compared to the First World War. Commercially, fermentation is still the major route for penicillin production. This is part of the culture laboratory at Beecham's, where the process starts. This large bottle contains corn, sterilized to remove all bacteria and molds. The bottle is carefully inoculated with spores of the penicillin fungus. The air we breathe is full of all sorts of microorganisms, and the sterile conditions are designed to exclude them. Otherwise, we could easily get a fermentation that produced no penicillin. After a few hours incubation, there's no obvious change. But after 2 days, the corn is white with fungus. Green spores start to appear as the nutrients in the corn are used up, and after 8 days, the corn looks like this. There are now sufficient spores to begin a larger scale fermentation. The spores are washed from the corn and sucked up into an airtight metal container, still under sterile conditions. The metal can is then taken to the fermentation plant. Everything within the pipework is steam sterilized, again to prevent unwanted airborne microorganisms from getting in. And the penicillin spores are transferred to this large seed fermenter. Inside the fermenter are the nutrients, including the sugar glucose, and also the sodium salt of phenylacetic acid, so that the end product will be a specific penicillin, penicillin G. This is only a seed fermentation. After about 40 hours, the contents will be transferred to a giant 100,000 litre production fermenter. Routine cleaning and maintenance of such a huge vessel is a considerable operation, involving safety harnesses and oxygen monitoring equipment. Penicillin production starts to look like a very large-scale operation, until you remember that the yield of penicillin is only a few grams per litre, and that the fermenting mass will have to remain here for 8 days to achieve the best yield. After all, penicillin is only a byproduct. The main product is carbon dioxide. The fermented contents are filtered on a giant drum to remove the fungus, which is cut off the drum as flakes. After organic extraction and precipitation as its potassium salt, the penicillin G is washed and partially dried as it passes along this slow conveyor. Penicillin G, though, is just the starting material for a whole range of semi-synthetic penicillins. The intermediate in making these is 6-amino-penicillinic acid, 6-APA. The removal of the side chain of penicillin G is done enzymically. The enzyme, bacterial amidase, is embedded in minute beads of resin. The resin beads are stirred with the penicillin G solution for a number of hours until hydrolysis is complete. After extraction and drying, we have a pure chemical, 6-amino-penicillinic acid, derived largely from glucose. By carrying out different side chain reactions, the 6-APA is converted into a series of what are known as semi-synthetic penicillins. Currently, the most important of these is amoxicillin. Amoxicillin is the condensation product of 6-APA with acetone and a mixed acid anhydride. They make up the mixed anhydride on site in one of these reactors. It contains several hundred litres of acetone at very low temperature, to which the reagents are added. First a solubilizing agent, then a catalyst, and finally the main ingredient, a derivative of para-hydroxyphenylglycine. The anhydride preparation is another batch process, and this operation is repeated every 3 hours. When the cold anhydride solution reacts with the 6-APA, the product is amoxicillin. Amoxicillin is water-soluble. Most of the impurities aren't, and are removed by solvent extraction. A crucial stage in amoxicillin production is to make sure that the mixture will settle into 2 phases, an organic phase at the top and an aqueous phase below. The heavier aqueous phase contains the amoxicillin. The amoxicillin is precipitated by acid, and the precipitate washed with water and organic solvents. All that remains now is to package the stuff. Amoxicillin has taken over from ampicillin as the most commercially important of the penicillins. Beechams are working flat out to meet the large demand for the product. Amoxicillin is lethal to many bacteria. But most microorganisms don't produce antibiotics. In the absence of oxygen, they ferment sugars to give ethanol, a familiar process to brewers and winemakers. But can it be scaled up and adapted by the chemical industry? In Brazil, large-scale fermentation of sucrose is already a reality. The quantity of ethanol they can produce is orders of magnitude greater than the quantity of penicillin we've just seen. These are the fermenters, and unlike most alcohol fermentations, this isn't for drinking. It's purified by distillation and used as a fuel. Some cars have been modified to run on alcohol alone, but even a conventional engine will run on fuel containing up to 25% ethanol, so-called gasohol. This is part of a program designed to reduce dependence on imported oil. But the ethanol could, in principle, be used as a chemical feedstock. It's easy to convert it to ethylene, for example. So, is sugar one of the answers to the question, where from next? Tate & Lyle's former research chief, Professor Chuck Vlytos.
You can use sugar in fermentation, not just to produce alcohol, but to produce a wide range of highly priced chemicals, which will be in great demand in the future, which at the moment, many of these are produced only from petrochemicals. And I think it's a very important question to ask ourselves, where will all the chemicals that we're used to today come from in the future? When we run out of petrochemicals, where will they come from? You can't produce chemicals from nuclear energy. It just doesn't happen. You have to have an alternative energy source. And the only one I can think of at the moment is, in fact, plant material, whether that be cellulose or sugar, trees or sugar crops, doesn't matter. But we have to begin today to do that research.
One line of research Tate & Lyle tried was to investigate the properties of sucrose in its own right, rather than converting it to ethanol. They found that by esterifying sucrose with fatty acids, they could produce a useful range of products, such as detergents and barrier creams. But Tate & Lyle's chemical research activities have already been cut back in favour of more pressing short-term developments. The commercial development of sucrose as a bulk feedstock for the chemical industry is still a long way off. While oil and gas are cheap, inertia prevails. We may know where our feedstocks could come from, but it'll probably take another crisis before we do much about it.